So in this session, we would like to consider doing a chi-square test. We have our basic question whether uh, younger elderly are more likely to fall than older elderly. So we have our falls data, and in our first step, we want to propose our hypotheses, and so our null hypothesis is that there is no difference in propensity or probability of falling between younger elderly 65 to 74 compared with older elderly 75 and older. The alternative hypothesis is that there is a difference in probability of falling between younger elderly and older elderly. So there are hypotheses, and here's our data in our cells, so that our first cell is younger elderly who fell. This is a compilation of fall statistics, so we have 8,369. Among the younger group, 31,898 didn't fall. 75 plus, 9,277 fell, 9,277 didn't. So from our basic contingency table, our basic 2x2 crosstabs table, we label these cells A, B, C, and D. We total the total for the younger group by summing those. So A plus B is 40,267. That's the total number of younger folks we have. If we tally up the elderly group, the older group, we have 18,544. So this is C plus D. Let's tally up the falls. That's A plus C. Tally up those who didn't fall. That's B plus D. And so younger plus older is the total 58,821. If you want to do a double check, those who fell, those who didn't, same number. So mutually exclusive, collectively exhaustive, and here's our total, 58,821. Now, what are our marginal probabilities? The marginal probabilities of young is the total young which is A plus B divided by the total. The probability of being old is C plus D, the total number of our elderly, or of our older, divided by the total. The probability of fall is A plus C over our total. The probability of no fall is B plus D over our total. So if we want to calculate these, A plus B divided by total, 68%, 68.5 technically, C plus D over our total, 32%, or 31.5. Those add to 100, as you can see. Probability of a fall, oops. So falls divided by total. So the probability of a fall is 30%. And probability of no fall, didn't fall over the total, that's 70%. So those give us our marginal probabilities. So we just took our margins and added by the total for our marginal probabilities. What about conditional probabilities? Well, the probability of a fall given young, A over A plus B. So the probability of a fall given young is the fall for the young divided by total number of young. Probability of no fall given young is young people who didn't fall, so that's B divided by A plus B. The probability of fall given old, so it's C. That's if the people who fell, and the total number of old people are C plus D. The probability of no fall given old is D, C plus D. So let's clean up some mistakes here. Okay, let's calculate our conditional probabilities. So we have A divided by A plus B. We have no fall divided by total young. Oops. So B divided by A plus B. We have the probability of a fall given old. So that's 50-50, right? Shall we put these in percents? Would be easier to see. And these add to 100. So the probability didn't fall. Oops. Probability didn't fall given older, 50%. So these are our conditional probabilities, A over A plus B, etc. Okay, so our odds ratio is the probability of fall given young probability of fall given young divided by probability no fall given young probability of fall given old divided by the probability of no fall given old. So if you multiply those out, you get a, put an equal sign here, a divided by a plus b divided by b over a plus b all divided by c over c d d over c plus d. So these cancel out. The c's plus d cancel out. And so we have a over b divided by c over d, which equals a times d divided by b times c, and that's our odds ratio right there. Now note that in Monroe this is erroneously stated, which is part of the reason that I wanted to derive it for you here. So odds ratio we've got a times d divided by b times c, and we'll go over here and do it, plus a time, whoops, plus a times d divided by b times c, oops, I'm sorry, did some of that wrong. A times d divided by b times c, and our odds ratio here is 0.26. So that's the odds of falling given young over the odds of falling given old. So 26% chance of falling if you're young compared to old, and the odds of falling if you're old compared to young. odds of odds old fall is 1 divided by the odds young, and that's 3.81. So there's our odds ratio. Next step here is to do our chi-square test. So as you recall, to do the chi-square test, in the first step, we developed our hypothesis. No difference in propensity or probability of falling. Alternative, there is a difference. Step 2 is alpha level critical value, and here let's let alpha equal 0.05, and we want to look at the chi-square table. So it's in Monroe, table L, distribution of chi-square. This is a simple one. Remember, our degrees of freedom are the number of degrees of freedom in columns multiplied by the rows. So we have 2 columns, so it's 2 minus 1 since we're doing the chi-square statistic. So it's the degrees of freedom column, 2 minus 1 are 1. Degrees of rows, 2 minus 1. 1 times 1 is 1. So our degrees of freedom equals 1 times 1, or 1. We go over to the probability distribution of chi-square, 0.05, 1 degree of freedom, 3.841. So critical chi-square equals 3.841. Can highlight that. Okay, so let's compute our chi-square, our expected value, and then we'll compute our chi-square statistic. So we come over here. Our expected value for the frequency in cell A is A plus B times A plus C divided by A plus B by our total. And so we'll do A plus B, which is here, times A plus C, which is here, divided by our total, which is here. And so we get 12,000 for our expected value of A. We do the same for B, expected value of B, so we have A plus B again, times B plus D this time, and that's the didn't column, divided by the total, and we have 28,000 for our expected values for B. How about C? We have C plus D times A plus C, which is our fall column, divided by our total, and expected value of D. So we have C plus D, again that total times B plus D divided by total. So that gives us our expected values. So next step, let's subtract observed minus expected. So the observed for A is here minus the expected observed in B minus expected. Note that they cancel out. Observed C minus expected. Observed D minus expected. And now we square those values. Don't have enough space here. And we divide our squares. By our expected. And sum them. And we get 5,162.83, which is our chi-square observed and our calculated. And that's far and away above the critical chi-square, so we reject our null hypothesis. That there is no difference in age groups in terms of odds of falling. We accept the alternative. That there is a significant difference in the odds of falling, and that difference is statistically significant. So all told, that's how we do this by hand. Not all that complicated, although complicated enough you probably don't want to do it yourself. So what? Let's do this in SPSS once and see what we find. So we'll put our values in here. Variable 1 is fell. Variable 2 is didn't fall. So we'll take a look at our data, and our first our row 1 is old, row 2 is younger elderly, row 2 is older elderly. So let's do analyze. Crosstabs our rows. rows are 1 and 2. And so I'm going to end this at this point and come back because it's taking some time, and I want to do this on a separate one.